Hello everyone, how are you? I think all of you are fine. And how are you passing your days? Um, After uh, 5 weeks completion, we are now in week 6. Today we discuss about water quality requirements. Let's see about the water quality requirements. Okay, come to the point about water quality. The basic requirements of drinking water are that the water should be completely free of pathogenic microorganisms that can cause disease. That means the water should be completely free of pathogenic microorganism which is responsible for disease. The water should contain no element or compound in concentrations that can cause acute or long-term adverse effect on human health. Then it should be fairly clear and aesthetically attractive, that is, low turbidity and colors, not be saline to cause salty taste. So it should be clear and aesthetically attractive. There is no objection about the turbidity. So turbidity would be less or low, and color and turbidity should be low and not be saline to cause salty taste. Because if water contain salinity, then obviously it causes salty taste. Contain no compounds that can cause an offensive taste and odor. So the water should not contain such type of material that is objectionable or causes offensive taste and odor. And the water should not cause corrosion, scale formation, discoloration, or staining, not have a temperature unacceptable to the consumers. So it should be corrosion free. It should not scale formation, discoloration, that means color would not be changed, staining, that means there is no staining action here, and not have a temperature unacceptable to the consumer. So temperature would be in good form. Let's see about the impurities and their effect. The impurities present in natural water may be grouped into the following four categories. Number one, impurities of mineral origin, impurities organic origin, living impurities, and the last one is radioactive impurities. Now let's see effect of impurities present in water. That means there are different types of impurities. If this type of impurities are present in water, then what happened? What happened on water and what happened on human health? So we use here different types of impurities along this column, and effect on water along this column, and effect on health along this column. Living impurities such as bacteria, viruses, algae, protozoa, fungi. Uh, so what happened? Bacteria on water, that is turbidity at high concentration, and on human health, disease. That is, bacteria causes different types of disease on human health or health. Viruses, it also causes disease, algae, protozoa, fungi. It causes turbidity, odor, color on water, and disease, toxicity on health. In a similar way, you can easily find out these types of impurities, what are the effect on water and effect on health. and here also radioactive impurities which causes disease on human health. Now, impurities of mineral and organic origin, silt and clay, salt or calcium, magnesium, salt, sodium, fluoride, nitrate, iron, manganese, arsenic, lead, heavy metals, vegetable dyes, etc. And there are a lot of effects on water and health. You can easily find out it by reading. You can understand it easily. Now, source and significance of selected water quality parameters. First of all, you have an idea about water quality parameters. Water quality parameter means that types of parameter which control the water quality, such as pH, color, turbidity, fecal coliform, TDS, etc., which control the quality of drinking water or any types of water. So we should know the source and significance of selected water quality parameter. Let's see first of all pH. What do we mean by pH? pH is a term used universally to express the intensity of acid or alkaline condition of a solution. That means if uh, we provide a solution of water, so you have to find out it is alkaline or acidic. So if you measure the pH of this type of water or solution, you can easily find out the value of pH, and you can you can indicate the acidity or alkalinity of that type of solution. It is a measure of the concentration of free hydrogen ion in water and expressed as pH is equals to minus logarithmic of hydrogen ion. The pH of an aqueous system is a measure of the acid-base equilibrium acid by various dissolved compounds, and in most natural waters is controlled by the carbon dioxide, and that is controlled by this equilibrium system. In most raw water sources, pH lies within the range 6.5 to 8.5. That is, in our country, BD standard of pH is equals to 6.5 to 8.5 is the range of pH for BD standard. In water supply, pH is important for coagulation, disinfection, water softening, and corrosion control. In biological treatment of water, pH is very important as the organism involved in treatment process operate within a certain pH range. Dissolution and mobility of metal in natural waters are also greatly influenced by the pH of water. So, you should know about the pH for our drinking standard according to environmental conservation rule. So, our country define it define the range from 6.5 to 8.5 for pH for drinking purposes. Let's see about the color. Color in water is primarily due to the presence of colored organic substance, primarily humid substance, metals such as iron, manganese, or highly colored industrial wastes. The supply of visibly colored water may lead consumers to seek an alternative colorless source of water for aesthetic reasons. Aesthetic means from the sense of beautification. So obviously, when you drink a glass of water, if the water is colored, then you have a bad impression, or you do not choose to drink this type of water if the water contains some color. So obviously, it should be colorless for aesthetic reason. Limiting the color in potable water means limiting the concentration of undesirable substances that are complex with or absorbed onto humid substances. Color caused by suspended matter is defined as apparent color. So apparent color comes from suspended matter and can be removed by centrifugation or filtration. Color caused by dissolved matter is defined as true color. So true color comes from dissolved matter. One true color unit, that is TCU, correspond to the amount of color exhibited under the specified test conditions by a solution containing 1 milligram of platinum per liter of water in the form of chloroplatinate ion. Most consumers can detect a color of 15 TCU, that is WHO guideline value, and Bangladesh standard for drinking water also in a glass of water. That means according to WHO and also Bangladesh standard for color is equals to 15 TCU, that is 15 to color unit. Now comes to the point turbidity. Turbidity occurs in most surface waters due to the presence of suspended clay, silt, finely divided organic and inorganic matters, plankton, and microorganisms. The suspended particles that cause turbidity range in size from colloidal dimensions approximately 10 mm to diameters in the order of 0.1 mm. Turbidity is an expression of certain light scattering and light absorbing properties of a water sample and depends in a complex manner on such factors as the standard method for measurement of turbidity employs the principle of nephelometry and measures the scattering of light from particles. Results are expressed in nephelometric turbidity unit, that is NTU. A turbidity in excess of 5 NTU is generally objectionable to the consumer. That means the value of turbidity if exceed 5 NTU, then this type of water is objectionable to the consumer. It can protect microorganisms from effects of disinfection, stimulate the growth of bacteria, and exert a significant chlorine demand. So, the drinking water should be free from turbidity, and it's obviously contain the value of turbidity below 5 NTU. Now, total dissolved salts, that means TDS. Total dissolved solids comprise inorganic salts and small amounts of organic matter. The common dissolved mineral salts are claimed to affect taste, hardness, corrosion, and incrustation. Dissolved dissolved inorganic substances may exert adverse effect on aquatic animals and plants and may cause irrigation problems. The amount of dissolved solids present in water is an important consideration in its suitability for domestic use. In general, water with a total solids content of less than 50 mg per liter are most desirable for such purposes. Waters with a higher solids content often have a laxative and sometimes the reverse effect upon people. Depending on the TDS, water often classified as follows. That means, depending on the value of TDS, we can define water in different categories. That means, if the value of TDS is smaller than 300 milligram per liter, then it would be excellent water. If it ranges from 300 to 600, then it is to be good, and for 600 to 900 it is to be fair. For 900 to 1200 milligram per liter it is to be poor, and if it exceeds uh, 1200 milligram per liter, then it is unacceptable. Then it is greater than 1200 milligram per liter, then it is obviously unacceptable. Another parameter is alkalinity. Let's see about the alkalinity. The alkalinity of water is a measure of its capacity to neutralize acid. That means uh, the capacity of neutralize acid is called the alkalinity of water. The alkalinity is due primarily to uh, salts of weak acid and strong bases as substances act as buffers to resist a drop in pH resulting iron acid addition. Alkalinity is thus a measure of the buffer capacity. Most of the alkalinity in natural waters is caused by three major classes of materials, that is bicarbonate, carbonate and hydroxides. Bicarbonate represent the most common form of alkalinity since they are formed in large quantities from the action of carbon dioxide upon basic materials in the soil. Another important parameter is iron. Iron in surface water is generally present in the ferric state. That means uh, here another form is ferrous, and here is ferric. That is here a power of iron is 3. The presence of iron in natural waters can be attributed to the dissolution of rock and minerals, acid mine drainage, landfill leaches, sewage, or discharge from iron-related industries. Iron in water may cause hardness, undesirable taste in beverages. Staining iron in water may cause hardness, undesirable taste in beverages, staining of clothes and plumbing fixtures, incrustation in water main. Incrustation uh, in water main means there is a layer in water supply pipe. This is called the incrustation, and may impart a reddish brown color to water. Iron in water is frequently accompanied by heavy growth of iron bacteria, which exaggerate the staining, pipe clogging, and other problems. Another parameter is hardness. What do you mean by hardness of water? Hard water are generally considered to be those water that require considerable amount of soap to produce a foam or lather, and that also produce scale in hot water pipes. So hard water would be that water which needs more uh, amount of soap to produce foam or lather. Now it produces scale in hot water pipes, heaters, boilers, and other units in which the temperature of water is increased materially. Hardness is caused by multivalent metallic cation. Such cations are capable of reacting with soap to form precipitate and with certain anion present in water to form scale. The principal hardness causing cation are divalent calcium and magnesium, strontium, ferrous iron, and manganese ions. Groundwater is generally harder than surface water. The Bangladesh Drinking Water Quality Standard recommend hardness between 200 to 200 to 500 milligram per liter based on taste and household use consideration, when the alkalinity value is usually close to the hardness value. Another parameter is chloride. Chloride is widely distributed in nature, generally in the form of sodium chloride, potassium chloride, and calcium chlorides, occur in, occur in natural waters in widely varying concentration. Sea and ocean water represents very high chloride levels. Uh, Test threshold for chloride are in the range of 200 to 203 milligram per liter. High chloride concentration are corrosive to metals in the water distribution system, particularly in water of low alkalinity. A higher chloride content in inland water usually indicates sewage pollution. So, when higher chloride content in inland water, it obviously indicates sewage pollution. Now, total coliform and fecal coliform. The most common and widespread danger associated with natural water bodies such as rivers and streams is contaminated by sewage, by other wastes, or by human and animal uh, excrement. Fecal pollution of water may introduce a variety of intentional pathogens, that is, bacterial, viral, or viral or parasitic. These include bacteria causing typhoid fever, bacillary dysentery, and cholera, virus causing hepatitis, uh, polymyelitis, and gastroenteritis, protozoa, etc. And another important term is arsenic. Many arsenic compounds are water soluble, and thus contamination of water may occur. Most of the arsenic found in water derives from geological formation, industrial discharges, mining operation, the use of arsenical insecticides, and from the combustion of fossil fuels. The toxicity of arsenic compounds depends on the chemical and physical form of the compound, the route by which it enters the body, the dose and duration of exposures, etc. Inorganic arsenic is more toxic than organic arsenic. The concentration of arsenic in excess of allowable limits has been found in shallow tube well in many locations. The recommended allowable limit of arsenic is 0.05 milligram per liter in Bangladesh. So, according to Environmental Conservation Rule for Bangladesh standard, the arsenic limit is to be 0.05 milligram per liter. Here we provide a chart for drinking water standard. First of all, serial number, then water quality parameters. There are a lot of parameters. Unit is mentioned here, this standard is mentioned here, and also rule guideline according to 1993. So you can easily mm, understand it, that is for arsenic, and the unit is to be milligram per liter. The standard is 0.05, and for gold standard 0.01. So you can easily understand it. Let's see the next slide. There is also another parameter for water quality parameter. This called water quality parameter. Now hardness, we have already we have an idea about hardness. Now we try to solve some problem regarding hardness. So let's see again the topics about the hardness. The term hardness is defined as the ability of the water to cause precipitation of insoluble calcium and magnesium salt of higher fatty acid from salt. The hardness or soap-destroying power of a water is of two types: temporary hardness and permanent hardness. The temporary hardness is also known as carbonate hardness, and it is mainly due to the presence of bicarbonate of calcium and magnesium. It can be removed by boiling or by adding lime to the water. The permanent hardness is also known as the non-carbonate hardness, and it is due to the presence of sulfates, chlorides, and nitrates of calcium and magnesium. It cannot be removed by simply boiling the water. It requires special treatment of water softening. Thus, the hardness of water is divided into the following two forms: carbonate hardness and non-carbonate hardness. Thus, you get the following relation, that is total hardness is equals to carbonate hardness or alkalinity plus non-carbonate hardness. Following two rules should be recommended in this connection. When alkalinity is smaller than total hardness, then carbonate hardness is equals to alkalinity, and if when alkalinity is greater than total hardness, then carbonate hardness is equals to total hardness. So it's mainly depends on alkalinity. So if alkalinity is smaller than total hardness, then carbonate hardness is equals to alkalinity. If alkalinity is greater than total hardness, then carbonate hardness is equals to total hardness. The hardness is normally expressed in terms of calcium carbonate. Now, the chemical analysis for individual ions are usually given in terms of that ion. It will thus be necessary to convert the analytical result to the common denominator. That means if you want to find out the hardness in milligram per liter as calcium carbonate, so you can easily find out that is N double plus here, that is ionic form, milligram per liter multiply with equivalent weight of calcium carbonate divided by equivalent weight of uh, that material where M represents any ion or radical. So equivalent weight of that radical or ion. For solving problems on hardness, the following facts should be noted. That means later we see some problem regarding hardness. So uh, before that is means if you want to start a problem, you should carefully read this type of thing, because is the law to solve the problem regarding hardness. So let's see. The alkalinity will be caused by positively charged calcium ion, magnesium ion, and strontium ion, and negatively charged carbonate bicarbonate ions only. The readings of other metals should be ignored. And also here we provide the equivalent weight of calcium, magnesium, and strontium. And also for measuring alkalinity, the reading of carbonate or bicarbonate will required and expressed as a percentage. They can be find out from the following relation. Total alkalinity as bicarbonate in milligram per liter is equals to bicarbonate alkalinity in milligram per liter multiplied with 1.22, and total alkalinity as carbonate in milligram per liter, then it is to be carbonate alkalinity in milligram per liter multiplied with 0.60. And here we provide molecular weight of bicarbonate is equals to 1 for hydrogen, and the molecular weight of carbon is equals to 12, and oxygen for oxygen it is 16, and there are 3, a number of 3 oxygen, then we multiply here 3, then it is to be 61, and in the similar way molecular weight of carbonate is equals to 60. Let's see the problem 1. The analysis of water from a board shows the following results in milligram per liter. That means calcium is to be 60, magnesium 48, sodium 103.5, potassium 19.5, bicarbonate is equals to 244, sulfate is equals to 220.8, chloride is equals to 78.1. Now find out the total hardness, carbonate hardness and non-carbonate hardness. Let's see the solution. Total hardness is equals to here the radical or ion is first of all 60. Then you multiply with 60, multiply with uh, molecular uh, weight of calcium carbonate, that is to be 50, divided by the molecular weight of the cation is to be 20, plus for magnesium is equals to 48, molecular weight for calcium carbonate is equals to 50, divided by molecular weight of magnesium is equals to 12.2. So here only calcium and magnesium come for total hardness, because we have already mentioned hardness comes from calcium, magnesium, strontium, etc. So there are no strontium ion here. So for hardness calculation only calcium and magnesium comes here. So 346.72 milligram per liter as calcium carbonate. Now, the total alkalinity as a bicarbonate in milligram per liter is equals to bicarbonate alkalinity multiplied with 1.22. So from here, we can find out easily bicarbonate alkalinity is equals to 200 milligram per liter. Since the value of alkalinity is smaller than the total hardness, so the carbonate hardness is equals to alkalinity, that is equals to 200 milligram per liter. So the non-carbonate hardness is to be total hardness minus carbonate hardness. So by subtracting 200 from the total hardness, that is 346.72, we can easily find out the value of non-carbonate hardness, that is to be 146.72 milligram per liter. Let's see the problem number 2. The analysis of a sample of water shows the following results in milligram per liter: sodium 20, potassium 30, calcium 5, magnesium 10, chlorine 40, bicarbonate 67, sulfate 5, nitrate 10. The concentration of strontium is equivalent to a hardness of 2.29 milligram per liter, and the carbonate alkalinity in this water is 0. Calculate the total hardness, carbonate hardness and non-carbonate hardness in milligram per liter as calcium carbonate. Here for total hardness, first of all comes calcium multiplied with 50, that is 50 stands for molecular weight of calcium carbonate, and 20 is the equivalent weight of calcium. For hardness calculation, after calcium, magnesium comes here. For magnesium it is to be 10, so here we put 10, and for calcium it is to be 5, and the concentration of strontium is equivalent to a hardness of 2.29. That means the concentration of strontium is equivalent to hardness of 2.29. That means there is no need here to find out the equivalent weight of strontium, because the value is already given here 2.29. So you can just adding this portion here for total hardness purposes. After calculation, total hardness is to be 55.75 milligram per liter as calcium carbonate. Now, bicarbonate hardness is equals to be 67 divided by 1.22, because 67 comes from here. Bicarbonate 67 and 1.22, you can easily find out bicarbonate alkalinity from here 54.92 milligram per liter as calcium carbonate. If you have any difficulty to solve this type of problem, just read the rule to solve this type of problem. We have already discussed previous 2 slide or 3 slide. Now, in this case, if alkalinity is smaller than total hardness, then carbonate hardness is to be alkalinity, that is 54.92 milligram per liter as calcium carbonate. Then non-carbonate hardness is equals to total hardness minus carbonate hardness. So you can easily find out non-carbonate hardness as 0.85 milligram per liter as calcium carbonate. Now, another important fact we have already discussed about pH value. Now, we try to understand about the pH value in details, and we try to solve some problem regarding pH value. Let's see. The acidity or alkalinity of water is measured in terms of its pH value or hydrogen ion concentration. You can easily find out or easily understand by reading this question. I have just already touching the big point. When water dissociate, then it produces hydrogen ion and hydroxide ion. Now, if the value of K, if we try to find out the value of K, that is constant, then we can divide the concentration of hydroxide ion multiplied with hydrogen ion divided by the concentration of water, and the brackets indicate the concentration of constituent in moles per liter. A mole is the molecular weight in gram. Since the concentration of water in a dilute aqueous system is essentially constant, it can be expressed as follows. That means Kw is equals to hydrogen ion concentration multiplied with hydroxide ion concentration, where Kw is equals to ionization constant or ion product of water. The multiplication of hydrogen ion concentration and hydroxide ion concentration is to be 10 inverse 14 at 25 degrees centigrade temperature. And if you want to find out the value of pH, that is to be minus logarithmic of hydrogen ion concentration, and from here you can easily find out the pOH. Now, hydrogen ion concentration and hydroxide ion concentration is to be 10 inverse 14, and from this point you can easily find out pH plus pOH is equals to 14. Here we provide the scale of pH. That means it ranges from 0 to 14, and 7 the value of pH. If the value of pH is equals to 7, that means it indicates that the water is neutral. And if the value of pH is smaller than pH, which leaves the solution is acidic, and if the value of pH is greater than 7, it also indicates the value of pH indicates the solution is alkaline. Let's see problem number 3. In the water treatment plant, the pH values of entering and leaving water are respectively 7.5 and 8.5. Assuming linear variation of pH with time, find out the average pH values of water. That means one types of water is coming in water treatment plant, that means entering, and the value of pH of entering water is 7.5, and the living water, the pH value of living water is 8.5. Now we have to find out the value of average pH. Let's see. By definition, pH means minus logarithmic of hydrogen ion, not hydrogen, sorry, here it is to be hydrogen ion. For entering water, pH is equals to 7.5. So 7.5 is equals to minus logarithm of hydrogen ion. So here not hydrogen, here is to be hydrogen ion. Hydrogen ion is equals to 10 inverse 7.5. And also for living water, pH is equals to 8.5, and also here hydrogen ion is to be 10 inverse 8.5. If we average the value of hydrogen ion, I reminder you again and again, it is not hydrogen, it is to be hydrogen, it's my mistake. So average values of hydrogen ion is to be uh, this value plus this value divided by 2, and it is to be 5.5 multiplied with 10 inverse 8.5. So the average pH value of water is to be minus log 10 hydrogen ion. So if you put the value of hydrogen ion from here, then it is to be 7.7596. Now problem number 4, calculate pH and pOH values. Here it is to be pOH values of freshly prepared distilled water. It's my typing mistake, sorry for that. Calculate pH and pOH values of freshly prepared distilled water. That means if you have distilled water, then you have to find out the value of pH and pOH. As per definition or equation, hydrogen ion concentration multiplied with hydrogen ion concentration is equals to 10 inverse 14 mole per liter. In freshly distilled water, the concentration of both ions will be same because the water is distilled. Here, hydrogen ion concentration and hydroxide ion concentration will be same. So, let's see. Let's consider both ion concentration is C mole per liter. So C multiplied with C is equals to 10 inverse 14. That is C is equals to 10 inverse 7. So hydrogen ion is equals to 10 inverse 7, hydroxide ion is to be 10 inverse 7. So pH is equals to minus logarithmic of uh, hydrogen ion. So minus logarithmic 10, hydrogen ion concentration into 10 inverse 7, 10 inverse 7, and from this position log 10 base 10 is equals to 1. Then this power uh, uh, comes this position, that is this minus is comes here and this power comes here, and log 10 10 is equals to 1, that means log 10 base 10 is equals to 1. So from this position we get minus minus plus, that is 7. Similarly POS is equals to 7. And these are all about your lecture 6, that means week 6. uh, Here we discuss about different types of water quality parameters, and we have also provide in this lecture about BD standard and WHO standard. I think you are able to understand all these type of things. Today is no more. Stay safe. Keep safe the environment. Thank you everyone.